Hi there. I'm going to have you guys get your notebooks and title a new page, Introduction to Logarithms. All right, this video is going to be a little bit longer today, which is why your homework is super short and will only take about 5 minutes. We'll continue working on this tomorrow. But it's really, really important because this is how we're going to begin the next half of our unit, a logarithm. This is interesting. I've never actually explained it to an iPad before instead of a group of people, so we will see how this goes. I want to begin by looking at the graph of a logarithm. So we are going to look at the graph of y equals log of x. And I like looking at the graph because it really kind of lets me kind of see that behavior. It gives me some insights about the function and the way that it behaves. So over here, I'm going to make a big table, an XY table, and then we're going to make a graph over here, and we're going to sketch what the picture looks like, okay? So let's get our graphing calculators out, and let's start plugging in different values for our logarithm. So I'm going to go into my calculator. The log button is right next to the 7. And there's another type of log too, which is going to be this ln. We'll talk about it later, and which is below a log. So log and the natural log, which is what ln stands for, these are both your log buttons. Getting started though, I'm going to use what's called the common log, which is our log log next to the 7. Okay, I'm going to plug in log of 0. Right away, we begin with an error. I know my calculator says overflow error, but that's only because it's kind of a knockoff of a TI-84 calculator. So it's an error. Let's plug in log of, log of 0 gives me an error. Let's plug in log of 1, and I get 0. So that actually means that it's going to be my x-intercept. If I plug in log of 2, I get 0.3. So if you keep plugging in more numbers, you start seeing that these numbers are really, really small. I will not actually get to a whole number 1 until I plug in 10. So it takes 10 units out on the x-axis to finally output 1. I have to plug in 100 to finally output 2. So let's go into our table and kind of recap here what we've just were seeing. And you'll understand that a little bit better, I think, once you start understanding how to evaluate logs without a calculator. When I plug in 0, I actually output an error. And so what that means on my graph is that I'm going to have a vertical asymptote right here at x equals 0. I'm not allowed to plug in 0. I can plug in numbers really close to 0, but they can't actually be 0. When I plugged in 1, I outputted 0. This means that it is going to be my x-intercept. When I plugged in 2, I got a really small number. When I plugged in 3, I got a really small number. It wasn't until I plugged in 10 that I finally outputted 1. So when I plugged in 2, I got like 0.3. 3, 4, 5, 6, 7, 8, 9, 10. 10 units to the right, and I finally output 1. I have to go 100 units on the x-axis to finally output 2. Now this thing is increasing, but it's increasing very, very slowly, okay? It's increasing very slowly, which is actually the opposite of a different type of function we were just talking about. But if we think about end behavior, as your x's get bigger and bigger and bigger, your y values will also continue to approach infinity. It just does it incredibly slowly. So let's go back into our calculator, and I'm going to delete these out, and let's start plugging in negatives. That would be my next thing, is to maybe try plugging in -1. Now this says not a number. Again, this is like a knockoff calculator that I downloaded. Yours should just say error, okay? And if it doesn't say error, I need you to go into your mode, and I need you to come down here and go into real mode. We are not going to have imaginary logarithms. So click your calculator over to real mode, and this time when you do it again and I type in log of -2, I think yours actually says like non-real, but regardless, we get an error, and that is the point. So go back into our table, and I'm going to plug in -1, I get an error. If I plug in -2, again, I get an error. any negative number is going to give us an error. And so as far as the graph goes, we're just not going to plug in anything negative. It doesn't create another vertical asymptote. It just means that there is no graph to the left of x equals 0. Quick little note, though, we need to add is that we cannot take the log of a negative or 0, okay? This is going to end up being like another little red flag for us when we start solving equations, is we need to be careful that when we get an answer and we plug it back in and makes us take the log of a negative, we might end up getting extraneous solutions. So finally, the last type of numbers that we have not plugged in yet are going to be your numbers between 0 and 1, your positive fractions. So when I plug in log of 1/2, I get the same number as when I plugged in 2. It's just going to be the opposite. When I plug in log of 1/10, I output -1. When I plug in log of 1/100th, I output -2. And so I can plug in a really, really small number, okay? This would be 0.00000000, really, really close to 0. And you'll see here that I output -14. So let's finish up our table. When I plug in 1/2, I output -0.301. I'm going to start plugging in multiples of 10 here, and I start seeing that I output negative numbers. So what we can see with the negatives, it is not okay to plug in a negative to take the log of a negative, but if we take the log of a fraction, we will output a negative. So it's not okay to input, but we will output negatives. Again, we're going to have to understand a little bit better how to evaluate a log before we can understand why we output negatives. But if I go to 1/2, I output -0.301. If I output 1/10, I get -1. Here I get -2. So we're going to have a hard time illustrating this. Basically, what's happening is our graph is going like this. It's forever going to approach. We can get closer and closer and closer to 0, but we're never going to actually plug in 0. And so, quick note here about this behavior. Different kind of end behavior. As we plug in x's that get closer and closer and closer to 0, your y values are actually going to go towards -infinity. Okay, we'll output more and more negatives. So this little graph right here, what's happening is the entire thing is increasing. We start by increasing really, really, really fast. All of this happens between 0 and 1. And then once we hit 1, it starts increasing really, really, really slow. So this is what the log of x looks like. Well, this is actually the exact opposite of another kind of graph we looked at, which is an exponential. With an exponential, it crosses at 0, 1. And all the growth, it increases also. But it increases really, 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 really slow until finally we get to 1 and the graph increases really, really fast. So this would be like an exponential graph, 2 to the x power, okay? And you can almost see in the graphs that an exponential and a log, they are like reflections of each other. And what that means mathematically is that they are opposites. So I want to talk for just a second about that because this is kind of an important part, is that exponential functions and log functions, okay, they are opposites, which is not exactly the right mathematical term for these, okay? In math, they are called inverses. Now, we don't talk a whole lot about inverses in Algebra 2. We should, but we don't. You'll hear about it more in pre-calculus. You've dealt with inverses all along, okay? If I have +5, then -5, okay, is inverses because they undo each other. If I have x squared, then square root of x, that would be the inverse, because to undo x squared, we would take the square root of both sides. If I have x to the 4th power, then if I take the 4th root, then that undoes it. They're inverses. And so all of these are inverses because they undo each other. And that's what you are going to see with a logarithm and an exponent. If I start out with exponent form and I say that 10 to the second power is equal to 100, that is exponent form. I can undo this by taking the log of the output we just got of 100. So if I take that 100 that we just got and I take the log of it, it will make me go backwards, and the log of 100 is equal to 2, which we will go back when I explain this more and kind of explain that. And so what we can kind of see is these two operations undo each other. Well, what we need to learn how to do is how do I convert between exponent form and log form, which is what I want us to do next. Okay, this is probably going to be one of the most basic skills, but definitely the most important. We are going to convert between exponential and log forms. And we're going to make a big table. And so in our table, we are going to have exponent form, log form, okay? And I'm going to do this in a couple different ways. We're going to write this in symbols. Oops. We're going to write this in words, I often find helpful. And then finally, we're going to write it by making an example. Okay? So we're going to write this in symbols. We're going to make this in words, and then we're going to make an example. So go ahead, hit pause if you need to, but take a second to make this table. You know that if we were in class, I'd have a nice little cutout for you, but for now we need to make our own. Okay, so here we go. This is what exponent form looks like. It looks like a base raised to the x power equals a number y. When we go to write a log, which again, there are two types of logs that I'm going to talk about, we are going to use a common log log. It looks more familiar. I think it's better for now. Logs have a base, and the base is written as a little subscript number. Whatever the base of the exponent is, that's what the base of the log is. And we're going to basically take the number that the exponent equaled, and we're going to plug that into the log, and it will then equal the exponent. So I think one thing that's important to notice is that a logarithm always equals an exponent. In words, I take a base to an exponent, and that always equals a number. When I convert to log form, I write log, and again, the base of the exponent is the base of the log, written as a subscript. And I take the log of a number, and that takes me backwards, and that will equal the exponent. Okay? So then, finally, let's put all of this with some numbers. And so I'm going to actually start with a logarithm. If I have log base 2 of the number 8, that will equal 3. And what we need to understand for today is basically, what does this logarithm mean? Well, what it means is that we have base 2, I raise it to the third power, and that will equal the number 8. So we're going to do a lot of practice today. In fact, your homework probably will take 5 minutes. And the point of it is to get a lot of practice over and over and over with converting between exponent and log form. I want you, by the time you're done, I want it to be quick. I want it to be memorized so that we can then tomorrow continue our conversation with evaluating logs. All right, so now finally we need to talk about, there's two types of logs. And then we can get into some examples. Two types of logs, okay? There is what's called a common log. And there's what is called a natural log. And a common log is the log button in the calculator. That is what you can use a common log for, okay? Common logs have base 10. Base 10 logs is what we call a common log. And it's called a common log because it is most commonly used. Now, a natural log is going to be ln in your calculator, okay? And a lot of times when I write it, I will make it a lowercase ln, but an ln stands for a natural log. And these logs have base e, which is an irrational number. But I need to come back to that, okay? So let's come back over here and let's talk about our base 10 logs. So some logs have base 2, okay? Some logs have base 3, but some logs just say log of x, like what we saw in the beginning when we were making our graph. And if you don't see the base, this is going to be, actually, I'm sorry, I don't like the way I did that. It is assumed, if I don't see the base, that this is going to be a base 10 log, and that is assumed. Okay, so let's talk really quick about what it means when I say log of 100 is equal to 2. Well, again, I don't see a base, so it's assumed that it's going to be base 10. And as we just learned, what this means right here, what this means is that our base 10 to the what power? To the second power is equal to 100. It means this base to this exponent equals this number right here. Let's move on over to our natural log, okay? E is a famous irrational number, okay? Like pi. So pi is that other famous irrational number. The difference is pi can be discovered using geometry in a picture. E has to do with growth. It has to do with exponential growth. And what was found, okay, a long time ago in history was that when things grow naturally in nature, that their growth started to the growth factor started to approach this number e, which, let me get to it. What is this number e? Go into your calculator, and what you're going to see above ln, this natural log, is you'll see e to the x. That did not happen by mistake right there. So above natural log is this e, and you can raise it to the first power. And it does not happen by mistake that above a log, you're going to see 10 to the x power, because again, 10 to the x and log, common logs are opposites, e to the x and natural log are opposites. But go ahead and hit enter, and oops, where did it go? If I go ahead and hit second natural log to the first power and hit enter, we get this 2.718 number. So let's go back and kind of write this down. That e is approximately 2.718. It goes on forever. Now I need to keep going for the length of this video, but tomorrow you're going to watch a little video about what is e, and she does a pretty good job of trying to describe what this e is. Hopefully that helps. So when we go to write logs, instead of saying, okay, log base e of x, we don't write that in math. And in fact, to any math person, this looks really, really, really silly, but that's all that it really is. It's a log that has this famous base e. We don't write it as log base e. What we do is we write it as a natural log. Again, this is not in, this is a lowercase ln. I write it as natural log of x. Okay, so we say that it is the natural log of x. And one nice thing about the natural log is it always, always, always has the same base. When you use a regular log log, the base could be different. So that's going to be it for now as far as that goes. I'm sure I could talk for another 5 minutes trying to clear it up, but to tell you the truth, we just almost need to keep going, and we need to just keep working on these concepts as we see more and more problems. All right, let's get to some examples. I want you to convert to log form. So I'm going to take a second, and I'm actually going to just write out all of the examples. 36 to the 1/2 power equals 6. Our next example is going to be e to the x equals 7. And our last example is going to be 10 to the a equals b. So hit pause, write out these examples, and then let's go ahead and get to it. When I convert this to a log, I write log, okay? And the base of the exponent becomes the base of the log. Make sure that that looks like a little number. It's called a subscript. All right, so it's base 36. We take the log of the number 6, and that will equal the exponent 1/2, okay? This one, because of the e, all right, I'm going to essentially use the natural log. But what I tell a lot of students getting started is go ahead, I know it's more comfortable, go ahead and make it log base e of 7, and that's going to equal the exponent x. But what I need you to train you to do eventually is you cannot leave it like this. It doesn't look right. It's just not how you write it. It just looks incredibly weird and funny to anyone who understands math. Whenever you catch yourself doing log base e, we need to write the natural log of 7 equals x, which, to tell you the truth, is easier. So from now on, when your head starts thinking log base e, we're going to write ln, which is the natural log. Last example, I have log with base 10 of the number b equals the exponent a. But again, this looks funny to people. We don't write logs with base 10. So we need to get in the habit that if we ever have a base 10 log, we just write log of b equals a. And I get it. People say, but is it okay if we make it log base e? And I say, no. It's okay for you to in your first step, but then I want you to make the answer natural log. And then people say, is it okay to make it log base 10? Not really. Just write it, but then in your next step, change it up, make it log base, make it just a single log, because that's what the common log is. It's assumed to have base 10. All right, I don't know if that made any sense. Let's keep going. For example 2. I want you to convert to exponential form. So again, I've got a couple different parts here. Let's say we've got log base 2 of 1/8 equals -3. Part B, the natural log of 5 is equal to x. And for part C, we have log of 1,000 is equal to 3. Hit pause if you need to. Finish writing this down. All right, so let's work through these. In this situation, the base of the log is going to be the base of the exponent. So it's going to be the base raised to the exponent -3 is going to equal the number. Well, one thing I kind of like about converting to exponent form is when you're done, you can look at it and see if it makes sense. Yes, 2 to the -3 power is 1/8, so I feel pretty confident that we did this right. It's when we get into variables and stuff that you can't necessarily always check your work. So again, now I have the natural log. What I would recommend is knowing that the natural log has this irrational base e, okay? So when I go to convert it, it's going to be, sorry about that. When I convert it, it's going to be base e to the x power is equal to 5. And we're going to leave it just like that. Okay? Last one. When I convert this, again, when I don't see the base of a common log, it's assumed to be base 10. And so when I convert this, it's going to be base 10 to the 3rd power equals 1,000, which again, I can tell is true. So to tell you the truth, if you're kind of tired of taking notes, this is actually probably a good place to stop. If you want, you can go ahead and stop and do page, I believe it's page 11 in your packet. And page 11 is just going to be a really quick practice of converting. Okay, you're going to look at it and say that it has 24 problems, but that's not really the case. What I usually do in class is when we get to this point, I stop, I hand you guys a paper, and I give you about 5 minutes, and I want you to almost do page 11 like it's a time test. I want you to convert, convert, convert. You're not solving anything, you're not calculating anything. Convert it, and by the time you're done, I want you going so fast that you are mindlessly converting between exponential and log form, and it feels like you're almost doing a time test, because this next part is going to be a little bit more difficult if you don't have completely memorized how to convert the forms. Okay, tomorrow we're going to end up doing page 12, which is evaluating logs and doing more work. So you could even hit the pause button and come back to examples 3 and 4 tomorrow. Or if you've got the time now, I'm going to keep going and we're going to do examples 3 and 4 right now. Okay, but you're not going to actually practice this until you get to tomorrow on page 12. But let's just keep going. Example 3. You are going to evaluate logs without a calculator. Okay, so I'm actually never really going to show you how to do this in a calculator. I suggest you don't learn because it's just going to create a temptation to do it the wrong way. So our first example is going to be log base 4 of 64. And I'm going to go ahead and write on here, we're going to do log base 5 of 1 over 25. And I really only have 2 more examples like this. I kind of take that back. We're not going to have an example 4. We're going to end with trying to figure out how to evaluate logs without a calculator. So here's what I do to get started, is I basically turn this into an equation, okay? I turn this into log base 4 of 64, and I put equals x. Because the point is, I don't know what it equals. That's what I'm trying to find. And so I write it as an equation. And then I convert the forms, and I convert this into an exponent. So what this logarithm means, it means base 4 to the x power equals 64. Well, a lot of times you're going to do this, and you're going to look at it and go, oh, I know what the answer is. I know that if I take 4, and I know that if I take 4 to the 3rd power, that will equal 64. And a lot of times we can just look at it and kind of figure it out, and we can tell what the answer is. So the answer to this is that this logarithm is equal to 3, okay? So log base 4 of 64 is equal to 3. Let's come down here. First thing I do, I take my log base 5 of 1/25 is equal to x. I turn it into an equation. The second thing that I do is I turn this logarithm into an exponent form because it helps me understand what the logarithm means. What it means is 5 to the x power equals 1 over 25. Some of you right away, you might look at this and go, yep, I know exactly what x needs to be. If you can't tell yet, you can always do a little bit more work and we can get common bases. I can change the 25 into 5 squared. I could then say that 5 to the x power, I could flip this into the numerator if I make it 5 to the negative 2. So now that I get common bases, I can see that x is actually equal to negative 2. So we say log base 5 of 1/25 is equal to negative 2. What we're really doing is saying 5 to what power gives us 1 over 25. And a lot of times people can kind of tell by looking once they understand that. Let's look at a couple more problems that maybe we can't just tell by looking. So again, this is still going to be example 3, but let's look at 2 more. Natural log of square root of e. And finally, for part D, let's say we have log base b of 1 over the cubed root of b, okay? And you have to understand too, go ahead and write this down. Even if you can tell what it looks like just by looking, that's not the point. You're going to have to show me a couple steps on your progress check. If I tell you to evaluate the log and you just give me an answer, you're not going to get full credit. I want to see you turn it into an exponent, show me the meaning of the log. All right, so again, natural logs, we know, have this base e. Okay, so I'm going to start by turning this, what was given to me, into an equation, because that's what I'm trying to find is what it equals. Natural logs are assumed to have this base e. I'm going to convert this to an exponent. So this means base e to the x power equals the number square root of e. So I don't blame you if you still look a little bit confused. So what I would recommend is let's get common bases. Let's make this e to the x, and let's change our square root of e, right, to the 1/2 power. And then once we get common base of e, we can then see, okay, x is going to equal 1/2. So this equals 1/2. So if we find the natural log of square root of e, it actually just equals 1/2 right there. All right, last example. Let's take log base b of 1 over cubed root of b and say that that equals x. I'm going to turn this into an exponent. The base b to the x power is equal to 1 over cubed root of b. Let's work with this. All right, I get it. Maybe it's possible that right now some of you are looking at it and you're like, I can tell what x equals. But the point of it really is to kind of show your thinking and show your steps. So let's just do a couple more things. Let's take our cubed root of b and turn that into b to the 1/3 power. Those should be some of your quick conversions right there. Well, I don't want b in the denominator, so to flip it to the numerator, I can say that it is base b to the negative 1/3 power. And finally, what you see is we've got common bases. We can set our exponents equal to each other. And we would say that this logarithm is equal to negative 1/3. Okay, so that's how we're going to go into it by evaluating. And what these little exercises do is they help you to practice converting, and they help you understand the meaning of a logarithm. So always make sure you show your steps. Okay, I'm done. Finally, those were long notes, I get it. It would be long if we were in class too. Let's recap. Today is Wednesday. So Wednesday, you basically were copy the notes into your notebook. That took a while, so the assignment is really, really short. Page 11, you're going to practice converting. This should take about 5 minutes. It's super short. Take a break. Come back to this on Thursday. On Thursday, okay, look back over example 3. I probably lost you a little bit because it was so long. You probably kind of got tired of listening. So look back over example 3, and we are going to complete page 12. Page 12 has a lot of problems again, but it's really pretty quick. And so again, this is going to be no calculator. I want you to show your steps. And I believe it even says it, you're going to check your work in the answer keys folder. All right. Good luck with everything. Please be in touch. Use Wednesday and Thursday to work on this whole logarithm thing, converting, evaluating, and I will be in touch because we're going to have on Friday, you are going to have a progress check. What is due is going to be pages 9, 10, 12, and 13, and you are going to have a progress check over all of this. Okay? Good luck. Bye.